So, okay, I hope you watched the previous episode on binary search. So, today we're going to solve a problem that is very much related to binary search, and I'll explain how you can modify this algorithm to suit that uh, algorithm. Okay, so I hope you know the binary search algorithm. I've explained this algorithm in my previous video. Now let's look at a problem that is related to binary search. Um, in this problem, you have an array, all right, and the elements of this array are either 0 or 1, but they satisfy a certain property that they are 0 until a certain point and then 1 after that, right? So it's 0 0 0 0 0 and then 1 1 1 1 1. So given such an array, you are asked to find index L such that f of, or rather a of L is equal to 0 and a of L plus 1 is equal to 1. Ideally, we want a transition point here, right? Where the values of the array transitions from 0 to 1, correct? So obviously the naive O of n approach is to do a linear search, correct, over this array. But ideally, obviously, arrays like this don't exist. But what do exist in practical problems is you have certain indices like 0, 1, 2, 3, 4, 5, 6, 7, 8, something like that. And then for each of these index, you can calculate a function value like f of 0, f of 1, f of 2, f of 3, and so on till f of 9. And let's say this function returns a boolean value, that is, these are the values. And we would like to find the transition point where if I go from index 4 to 5, that is the place where the functional value changes from boolean value 0 to boolean value 1, right? An example problem of this I would like to refer is called aggressive cows. Aggressive cows, you can look this up online, right? Usually this problem uses binary sort of this form. So we would like to solve this problem using binary search because this naturally falls in binary search, because let's say I end up, maybe I'll tell you how this is binary search. So given an array like this, 0 0 0 1 1, whatever. So this is L, this is R, correct? And we solve some M, this is M. So if I know f of, or array of M is 0, then I do have information that I can discard all this half, correct? This half from L to M I can discard. So this naturally falls under the binary search class of problems, right? So how do I adapt this algorithm that we have seen to this problem? That is the question we want to solve. So here an easy manipulation is that, let's suppose given an array of zeros and ones, right? I would like to find the element 0.5. Obviously, the element 0.5 does not exist in this array, but if you run this algorithm with this array and with this k, what you'll end up is two numbers L and R from the previous video, where array of L less than or equal to 0.5 less than array of R when the loop terminates. Basically, that means that L comma R form the transition points, correct? So all you need to do is basically k is 0.5, so 0.5 less than a of m, correct? But you can use the property that all these values are 0 and 1. So if an element is greater than 0.5, that element must be 1, right? So essentially you can replace this as array of m value is equal to 1, correct? Equal to 1. This is same as this condition. And so other condition obviously will be array of m equal to 0, correct? So once you replace this condition with this condition and this else condition, you don't have to replace anywhere, and run this algorithm, you'll end up with L and R that form the transition points. Correct? So yeah, this is a continuation of the binary search algorithm, and this is quite a common problem you see. Most of the problems that use binary search, some of them need this type of manipulation, and this specific manipulation of finding transition point is usually a tricky one, and many DSA problems require this transition points to be found, and aggressive cows in specific, the problem is one such problem. Maybe let's go into the aggressive cows problem and see how we can apply this transition point algorithm to aggressive cows and why it makes sense. So the problem of aggressive cows is very simple, or the formulation is simple, but the understanding is hard. So you are given an array. What this array represents is, from a starting point, there's a farmer who is building stalls, right? So he has built the first stall here, and then he has built the second stall after 3 meters from the first stall. That makes a total distance of 4, and so on and so forth. Maybe after 7 he has built something else, right? That'll be 10, and maybe after 12. So basically the index I represents distance of ith stall from start, right? Now you are also given a number n, which represents the number of cows, right? And let's suppose n is less than or equal to the length of array, right? This is a assumption. Now let's suppose what we want to do is we want to place these cows in these stalls. So for example, 1, 4, 10, 12, 15, 17, 19. So let's say n is equal to 3. I can place these 3 cows in multiple locations, correct? I can place them here, 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 and here. So multiple locations. So given any configuration where I place, I can calculate the maximum separation, right? For example, I placed it 4, 10, 12. I want to calculate the minimum separation, right? So cows 1 and 2 are separated by a distance of 6. Cows 2 and 3 are separated by a distance of 2, right? So the minimum distance in this configuration is 2, correct? Similarly, I can calculate for the next configuration, this configuration. I want to calculate what is the minimum distance. The minimum distance between 10 and 15 is 5. I mean, this distance is 5, and this distance is 4. So the minimum is 4, correct? So on and so forth, right? You can place all the cows anywhere possible, and then you get a lot of these numbers. And from these numbers, I want to return the maximum, right? From this maximum. So it forms a maximum minimization problem, which is you want to maximize something, and the something we want to maximize is the minimum distance between the two, between the cows, correct? This is the formulation, right? So seems a bit confusing, to be very honest. So the way to solve this is that let's solve it in O of n first, and then see how we can apply the transition point problem. To solve it in O of n is very simple. What we will do is, let's suppose we start with the minimum distance as 1, right? So what I want to do is, I'm asking the question, can I arrange all the cows, correct, all the cows, such that the distance between any of them is at least 1, at least 1, right? This is the question I'm asking, right? You can solve this question very easily. You can write a function wherein you place the first cow here, and then unless the minimum distance is 1, you won't place it, right? So you can place it almost everywhere. So these 3 are formed. So yes, I can place all the cows such that the minimum distance is 1. Now you ask the question, can I place them at distance 2? Can I place them at distance 3? Can I place them at distance 4? So on and so forth, until can I place them at a distance of the maximum possible distance I can place any of them is, let's say, 19 minus 1, which is 18, right? 18, correct. So I can ask these questions until 18, and what happens is at distance 2 I can place them, at distance 3 I can place them. So somewhere at, let's suppose, distance 9, what happens is distance 10, let's suppose I can place all the cows at distance 9. That is possible, right? But let's suppose at distance 10 it is not possible. Then I know that the answer is 9, because if I have to find a configuration where the minimum distance is 10, there is no such configuration, right? So out of all these configurations, I can find no configuration where the minimum distance is 10. Hence, the answer should be 9, right? Think about it a bit. I think it's not the most straightforward thing to understand. But what I really mean when the answer is 9 is I can place the cows such that, right, the minimum distance between them is 9, correct? And then I can place all the cows. But when I go to minimum distance of 10, I cannot place the cows, right? At least one cow will not be able to fit in, right? So that's what I mean. So this forms a very natural transition point algorithm, right? Because what we are saying is, for this array of 1 to 18, 1, 2, 3, so on 18, right? So some of them will be ones or zeros, whichever, right? And one, at some point there's a transition, and after that I cannot place these cows anymore, right? So now I want to find this transition point, and obviously I can do linear search, correct? The linear search here I can be done. It will be O of an algorithm, right? O of an algorithm. But if I do the transition point, it will be O of log n algorithm. And the difference is obvious because calculating this algorithm, right, given a distance d, is it possible or not, right? That question requires computation of some function f, which is very costly, right? So O of n algorithm is always better than O of n algorithm in this case. So this forms a very good illustration for the transition point algorithm. Obviously, you can apply this in various places, but remembering that you can apply this to find this kind of transition is very important, and I hope you understood that.